Hello, thanks for tuning in. Today I'm going to talk about a project from the Cake Lab at WPI that we call PieSlicer. The big idea is that mobile devices exist in an inherently dynamic environment and therefore must adapt dynamically to their environment. To this end, there's two big pieces to this work. First, we examine the mobile deep learning inference workflow and see how different pieces interact and show that each of these pieces can be accurately modeled. Second, we leverage this modeling to allow us to reduce response time in a real-world application. First up, some background and motivation. Our application space is that of image classification. An example of this would be an app that identifies this picture as being of a dog. We chose this space to demonstrate our approach because there's a lot of active research on image classification models. There's a lot of easily measurable input data. We haven't yet explored other kinds of deep learning, but we expect the same techniques can be leveraged in those fields as well. What does such a workflow look like? Let's break it down into a couple of steps. First, the input data is captured, usually by taking a picture with the device's camera. The second step is on-device pre-processing. This pre-processing consists of resizing and cropping the image. This step is optional because these steps can also be performed in cloud later on faster hardware. Next, we transfer the data across the network. If pre-processing was done on device, then the data transferred is small, on average 53 kilobytes. However, if in-cloud pre-processing is to be used, then the transferred data could be much larger. This can mean the difference in transfer time between tens of milliseconds and over a second. Step 4 is in-cloud pre-processing, which in addition to cropping and resizing also involves preparing the data for use by the model. The resources in the cloud are much more powerful than on-device, so pre-processing here can be much faster than on-device pre-processing. Finally, in step 5, the model is executed. There's been a lot of previous work on optimizing for this step and reducing execution time as much as possible. While this does reduce response time, it neglects the impact of steps 2 through 4, what we've referred to as the pre-execution time, on the overall response time. This pre-execution time can easily overshadow execution time. Here, we show the network transfer time and compare it to the execution time of two models, a very fast mobile net model and a very complex NASNet model. We see that for small files, the network latency can be less than the execution latency. However, when we consider larger files, more similar to those from mobile devices, the network transfer time can be an order of magnitude longer than execution time. The straightforward answer, assumed by many inference-serving systems, is to pre-process the data on device, but this comes at its own cost due to constrained resources on device. The cost of either network transfer or on-device pre-processing leads to a trade-off to be made, where different files would benefit from either on-device or in-cloud pre-processing. Here we show the pre-execution transfer time for each approach and see that there's a cutoff in file size where one approach is better than the other. However, even when we consider a single mobile device that switches between a wide range of networks throughout a single day, it becomes obvious that a dynamic solution is needed. To this end, we introduce PieSlicer, which uses simple and fast performance models to dynamically make pre-processing location decisions. PieSlicer is an Android library for image classification that considers the inputs and the environment and makes decisions about where to perform pre-processing in a dynamic manner. It aims to use performance models based on each step of each of the steps of on-device preprocessing, network transfer, and in-cloud preprocessing to estimate the pre-execution time of the on-device and in-cloud routes. It then decides to take the route that has the lowest estimated latency. We enable this by measuring the performance of each step in the deep learning workflow and modeling them. Our goal with these models is to be able to accurately predict the latency of each step within the pre-execution cycle. Remember that once we get to the execution, everything is the same. The input is the same and the format, so we're just interested in being able to consider the impact of different choices in the pre-execution steps. We have a few requirements for these models. First, goes without saying that we need them to be accurate. Next, we need them to be low latency to use. Finally, we want low overhead for training and usage. Based on this, we'll test 5 kinds of models for accuracy and then consider which is the best for our purposes. Our 5 model types are random forest, support vector regression, k-nearest neighbor regression, linear regression, and lasso. For each of these models, we give them 5 pieces of information: the original file size, the expected transfer size, the height, the width, and the resolution. We chose these pieces of data because they're fast and easy to get. 2 quick notes for those of you paying close attention. First, since we don't know the transfer size prior to deciding our path, we either use the original file size, or if calculating for the on-device path, we use the average file size of 53 kilobytes. Second, there is potentially an implicit correlation between height, width, and resolution, but we don't expect this to adversely impact our model performance. To collect our data, we used a range of devices, networks, and 2 custom data sets. These data sets, image 5K and image 1K, were pulled from Flickr to be more similar to real-world data than existing data sets, which are mostly used for training. Details on how we did collection can be found in the paper itself. Using our collected data, we trained our model types on subsets of data to see how accurate they could be. Again, details are in the paper if you want to check them out. The key thing we saw, though, was that in most cases, extremely simple linear regression models were as accurate as much more complex models. The only cases in which it wasn't as accurate as was when we were using a disparate data set, such as considering a single model that can predict regardless of which network is being used, which is a complicated use case. The only 2 models that did outperform linear regression models were KNN and SVR, which both either have high usage or training overhead, making them much less suitable for use on mobile devices. Therefore, we opted to use linear regression models in PieSlicer. So how well did PieSlicer use these models? To test this, we used a setup that was essentially similar to our measurement gathering setup. Same devices, same servers, same network. We tested each image from our image 5K dataset and recorded the response time. In addition to PieSlicer, we used 2 baselines and derived a third from these 2 baselines. The 2 baselines we used were static local and static remote, where we always pre-processed on device or in cloud, respectively. The derived baseline was static minimum, which for each tested image selected the minimum response latency of the 2 static baselines. This was essentially the best performance we could expect for each image, but all are still subject to real-world variations. First off, let's compare how PieSlicer did compared to this empirically designed base case. We see that it had an extremely high F1 score on all devices and all networks, above 0.98 in all cases. An F1 score is the harmonic mean of precision and recall, thus measures how well a classifier works. It ranges from 0 to 1, so our score indicates that we're doing an extremely good job classifying. Further, the average decision latency is only 330 microseconds, meaning that these decisions are being made extremely quickly. This shows that not only are our linear regression models effective, but they're also extremely fast, accomplishing both of our goals. We see that PieSlicer makes good decisions and makes them quickly. So what does this mean in terms of latency reduction? We see that PieSlicer outperforms our baseline in 14 out of 18 measured points, ranging across all models and all devices and networks. 2 points stand out in particular. First, at the 99th percentile on a residential network on a mid-end phone, we see the largest percentile improvement, a 16.5% reduction over the static minimum baseline. This corresponds to a pre-execution time of reduction of over 217 milliseconds, which exceeds the execution latency of many complex models. Second, the best median performance was an improvement of 6.6%, or just under 50 milliseconds. More details and delving into what we see at different levels can be found in our paper. Finally, one other advantage of using PieSlicer is that it can reduce the bandwidth usage over a static remote approach. This is thanks to pre-processing on device when it's advantageous to do so, allowing it to reduce bandwidth usage by over 98% in some cases and over 92% in all cases. So in summary, our goal was to consider the impact of different parts of the deep learning workflow for mobile devices. We identified that the pre-processing and network transfer steps, the pre-execution time, highlighted here as core to the response latency, and in fact making up a larger part of it than the execution latency. We then demonstrated that we can measure and model these components with high accuracy using simple and very fast models. We then use these models in a real-world system, PieSlicer, in order to reduce the pre-execution latency by dynamically making decisions regarding where to perform pre-processing. We've released our application for benchmarking in all of our modeling code so others can use it to benchmark their own deep learning applications or leverage PieSlicer within Android applications. For more details, please check out our paper, PieSlicer, Improving Response Time for Mobile Deep Learning Applications. And for other cool projects, check out our lab at cake.wpi.edu. All the code can be found at our GitHub website, github.com/cakelab/PieSlicer.